Hi everyone. Today let's talk about some of the trends that you can recognize if you take a closer look at the periodic table. And just like a lot of times in this unit, we're going to start our study by looking at some of the people who made this all possible. So there are four main people who have had a pretty big impact on the periodic table. You can see here we've listed them chronologically. So first off, we had Dobryner, who noticed that as you look at different elements, a lot of them share common properties. They have a lot of similarities between them. So maybe there's a way we could arrange those elements in such a way where we make more sense of that. And so Newlands was the first to do that, and he did it based on atomic mass. Now we're based on atomic number, but he also realized that there's kind of a periodicity where things, in terms of properties, repeat every eighth element. Dmitry Mendeleev is probably considered the father of the periodic table. He gets the most credit for arranging it. He has created the more modern day periodic table. He was actually able to predict some of the properties of elements that hadn't even been discovered yet. And he was able to do that because he realized if you arrange the elements in certain ways, then their properties become consistent. So for instance, as you go down a column on the periodic table, the properties all look very similar. And then finally, Moseley came along and arrived at our final arrangement of the periodic table based on atomic number, which is similar to atomic mass, but there are just a few places where atomic number actually solves some initial problems that we had with the periodic table. So what we're going to do today is look at several different characteristics or measurements and how they are impacted as we look at the periodic table. So first we'll talk about atomic radius. Atomic radius, quite simply, is the size of the atom, and you'll notice here that we have atomic number on the x-axis and atomic radius on the y-axis. And it's no surprise that as you go down on the periodic table, you get bigger, right? So as you go from one energy level to the next, as you go from, let's say, energy level 1s to 2s to 3s, right, you're getting bigger. So that's not very shocking. What is surprising is that as you go from left to right on the periodic table, aka the atomic number is getting larger, and you can see that right here, the atoms get smaller. So atomic number getting larger, atoms getting smaller as we go across the periodic table. Why in the world is that? And it has to do with the ratio of protons to electrons. So as you have a much greater number of protons as you go left to right across the periodic table, more and more protons, they are able to actually act like a magnet and kind of pull the electrons a little bit closer to them. And that's why the radius actually ends up decreasing. We call that nuclear force, because the attraction of those protons to those electrons becomes greater because there are more protons pulling on the electrons, and because the electrons are so far apart and because they are so light, those additional protons are able to pull them in quite a bit more tightly, and you can actually see this in the data that we've provided here. So the next trend we're going to look at is ionic radius. This is the radius of the atoms, but after they form an ion. And so this actually changes a little bit as you go left to right across the periodic table. So first off, again, as you go from the top down, things get bigger. And that's not all that shocking, right? You're adding energy levels. But look at what happens everywhere on the left of this staircase, right? This staircase is the kind of metalloid staircase where we divide metals from nonmetals. So over here on the left-hand side, we have metals. These ones form cations. They form positive charges by losing electrons. And so you'll notice that as you go across the periodic table from left to right, you again get smaller. And it's the same type of deal, right? As we lose more and more electrons, we have a higher ratio of protons for electrons. So very much like atomic radius, we have this higher ratio of protons to electrons that allows the remaining electrons to kind of get sucked in a little bit tighter towards the nucleus, which means ultimately that we get smaller as we go left to right. But the opposite is actually true on the right-hand side. So it turns out that as we are gaining electrons, remember these are the nonmetals, and over here, as you gain more and more electrons, like if you look at these three, the trend is pretty clear. As you gain more and more electrons, for instance, going from 1 electron gained to 2 electrons gained to 3 electrons gained, there are way more electrons for that same number of protons to try to hold together. So therefore, the ions get larger as you add more and more electrons. So really, ionic radius, as you go from left to right, in both cases, whether it's a cation or an anion, you're getting smaller going left to right. But it's kind of for different reasons, because in one case you're gaining electrons and in one case you're losing electrons. That takes us to ionization energy. So ionization energy is the energy that we need to remove an electron, and that's in order to form a cation, right? Cations are formed, they're positive when we lose electrons. And so this is how much energy it takes to remove one of those electrons. And so let's look first at going down a column, right? So up here you can pretty clearly see the noble gases. And you'll notice that as we go down a column, the noble gases, it requires less and less energy to remove electrons. Why is that? Well, it requires less and less energy because if you think about a noble gas like helium, where its electrons are really close to the nucleus, it's going to be really unhappy, that noble gas, with you taking its electrons. Not happy at all. But as those electrons get further and further and further away from the nucleus, they're more prone to be available to be removed. Now, noble gases in general really don't like you stealing their electrons, right? We know this. And so that actually helps to describe why, as you go from left to right across the periodic table, across a period, the ionization energy gets much, much higher. It takes way more energy to remove an electron from something like neon than it does to remove from oxygen or lithium or boron. Why is that? Well, remember, something like lithium has one extra valence electron. It's just sitting there, so it's ready to be taken. So if we drew the electron configuration for lithium, it would be 1s2, 2s2. This thing is 2s1, I'm sorry. Lithium is looking for an opportunity to get rid of its electrons. It wants to get rid of this extra electron, because if it can get rid of this extra electron, then it has a full sublevel, and it's happy with that. So it's really happy to give that up. Whereas if you look at something like neon, neon has a completely full 1s, 2s, and 2p. So there are electrons in every single one of these locations. So therefore, neon is really hesitant to give you that, right? You're going to have to pay a whole lot of energy to take away this electron, because if you do that, if we get rid of that, then neon is in a state where it could be 1 electron away, just 1 electron coming into that spot, from being really stable and having a full valence shell. So it's really not wanting you to do that. Therefore, it has a really high energy. It would take a lot of energy to steal an electron from it. The opposite of that is something called electron affinity. Electron affinity is basically when you form an anion, when you add that electron in, how good does that make the atom feel? So this is a little bit confusing to read, but basically as we go higher on this part of the graph, that means that the atoms up there are really happy if you give them an extra electron. So you'll notice all of your halogens up here. They're really okay with gaining an electron, right? So they all have a 2p, or a p sublevel in general, that looks like this, right? So they have an extra spot for an electron. So they're going to be really happy. They're going to release a whole lot of energy if you give them that last electron. Whereas something like sodium, right? Sodium has an s sublevel that has 1 electron. If you give it an extra electron, if you give it something here, it's not really happy with that, because it actually wants to get rid of this electron, because if it can get rid of this electron, then its new valence level is completely full. So it really wants to get rid of this one. If you give it another one, it's like getting further away from where it wants to be. So that's why it's really unhappy. It's down here. It's really unhappy with you trying to add an extra electron. And then finally, electronegativity. So electronegativity is the ability to attract electrons, but it's very specifically through a covalent bond. So if you have something like this, if you have hydrogen bonded to oxygen bonded to hydrogen, we know that, right? It's water. It turns out that oxygen likes electrons a lot more than hydrogen. But oxygen isn't just like a vacuum cleaner, like sucking in electrons from all over the place and pulling electrons towards it from all over the place. What it's doing is it's pulling electron density through this bond. So it's pulling a little bit of the electrons through the bond. It likes the electrons a little bit more than hydrogen. And so as you go from the left to the right on the periodic table, you'll notice the electronegativity gets higher as you go over here. And it also gets higher as you go from bottom to top. So we can use those trends to predict a little bit. I'm going to head to the periodic table. You guys can stay on your note guides. Let's predict some information, and let's list some of these elements in increasing order. So number one says we're going to list the elements from smallest to biggest, Ni, K, and Kr. So let me go circle all of those. And when I find Ni, K, and Kr, you'll notice that they're all in the same row. And that's very intentional. With all of these questions, we're going to keep elements in the same row or the same column so that we can compare directly, because it would be hard to compare something like nickel with something like aluminum, right? They're in two different rows, two different columns, so that's hard to compare. That's why we're giving you stuff that's all in the same row. So when it says the elements from smallest to biggest, remember atomic radius, we actually, as we go from left to right, we get smaller. So if we want to go from smallest to biggest, we're going to start with Kr, and then we'll come to nickel, and then we'll come to potassium. So for number 1A, Kr, Ni, K. Number 1B, it says we are going to deal with B, Al, and In. And remember, because we're adding energy levels, we get larger as we go down. So if we want to go from small to big, they're actually already in order. They are set up B, Al, In. Right? So the way we've circled them here, those are getting larger. Boron, aluminum, indium. And then for letter C, you'll notice we have circled some noble gases. So we are worried about helium, neon, and xenon. And that is the order in terms of size because we get larger as we go down. So the smallest to largest goes He, Ne, Xe. All right, let's try ionization energy, right? Ionization energy in number 2, we again are going to give you some stuff in the same column or row. So for instance, Be, Mg, and Sr. And remember, ionization energy, we said, gets larger as you go up towards the top. And ionization energy gets larger as you go from left to right. So how much energy does it require to take away an electron? Well, it requires a lot more on the left-hand side and the right, it requires a lot more at the top, and it requires a lot more on the right-hand side. Those elements don't really want to lose their electrons. So if we're going from an order of increasing, if we're going from smallest to largest, then we are going to start down with Sr, followed by Mg, followed by Be, because things that are down at the bottom are the smallest. Remember, my green lines up here are both increasing. We increase going from bottom to top. We increase going from left to right. So in order of increasing, we'd go Sr, Mg, Be. Let's try Bi, Cs, get a new color here, Bi, Cs, and Ba. And you'll notice we increase left to right. So if we want increasing order, we're going to go Cs, Ba, Bi. And finally, for ionization energy, let's look at Na, Al, and S. And we again said we increase left to right. So the order will be Na, Al, S, exactly how it's given to you. Finally, in electronegativity, remember electronegativity has a very similar trend to ionization energy. So it also is something that increases towards the top. It increases towards the right-hand side. Really, if we had to draw electronegativity, we draw a big arrow like this. It gets much higher as we go towards fluorine. And so if we circle 2 elements, these ones might not be in the exact same row or column, but if we circle 2, like lithium and oxygen, and we wonder which one has the higher electronegativity, that's definitely oxygen because it's way closer to the upper right. So you'd want to circle oxygen. In terms of Ca or Ra, there is your Ca. Ra is a little bit hidden. It's down here. It's a noble gas. So which one of those has a higher electronegativity? This one's pretty weird, right? So it looks like Ra is, I'm sorry, that is Rn. I apologize, radon. My fault. Ra is down here, radium. I've gone crazy. So again, those two are in the same column. So pretty clearly, calcium is going to have the higher electronegativity because it's closer to the upper right-hand side. And finally, as we look at potassium or vanadium, here is potassium, here is vanadium. As we look at those two, vanadium is closer to the right-hand side, so it's going to have the higher electronegativity value.